Hello from the Forcetronics YouTube channel, and welcome to building a wireless sensor network with the NRF24L01 transceiver module from Nordic. And this is probably going to be part one in a 3 to 4 part series. So let's get started. So the goal of this series or project is to create a scalable wireless sensor development board using the NRF24L01 transceiver module in Arduino. Why the NRF24L01? Well, I have plenty of videos on it. Everybody should know I like it. Also, it's low cost. The communication is reliable. And the goal here is when I'm finished here, I'm going to use this board in my home as a wireless sensor network. And then I'll provide you, the code, the parts, as well as the Eagle files to create your own. So I'm sort of making a reference design for you to leverage. And then also, I'll offer the development board along with the example code on my online store at forcetronics.com. So when I was researching this project, I found out this great library created by ManicBug. And ManicBug actually is one of the original creators of the Arduino NRF24 library. And he has this wrapper out there, the NRF24 network library. And what this does is it allows you to create a network where they almost are like Zigbee devices, where Zigbee uses sort of a mesh network configuration. The NRF24s will do that too. And if you have any experience with the NRF24s, you should know that built in, they can communicate between 6 modules, 5 transmitters, and 1 receiver. But this wrapper, this library network wrapper, allows you to create much larger networks, and it'll handle all the communication between the modules behind the scenes. It abstracts that from the user. And so I have this picture, and I actually borrowed this from ManicBug's website. There's his website up there. He has great content on there. I hope he doesn't mind I'm using his picture. But basically, you have 3 distinct positions, I should say roles in the network. The main one is 0, 0. This is the coordinator, and I'm going to use the terms that they use for Zigbee network. So that would be the coordinator, the one that's getting all the data in the wireless network. Then you have routers, and what a router can do is it can send data to the coordinator, but it can also take data from someone that's connected to it and pass it to the coordinator. Then you have the end devices. The end devices are sort of the things on the outer network, and they're not going to pass communication from other people, but they're going to take either communication from a coordinator or a router or send communication to a coordinator or a router. So one thing to note is the coordinators and the routers, because they are the ones passing the information along, they always have to kind of be on, whereas the end devices can actually go to sleep. And I'm going to show that in my code. Well, actually, I'm not going to show code here, but I'll use sleep later. So for instance, the coordinator, you'd want to have that plugged into a wall socket, and you probably would want your routers plugged into a wall socket, whereas your end devices can be battery powered and use very little power. And once again, the point of the router, you may not even need a router. You might just need a coordinator and end devices. The router is if your network is so large that some of the other devices can't be real close to the coordinator, so you have a router in between. And you can kind of see the numbering system that ManicBug set up in this example. So you'll actually use this in the code when you create these. You'll give them these addresses. So 0, 0 is going to be the coordinator, 0, 1, 0, 2, 0, 3, 0, 4, up to 0, 5 would be the end devices for that coordinator. And then if you wanted to add more end devices, you might have a 0, 0, a 0, 1, 1, and then all of a sudden 0, 1 becomes a router, not an end device, and 0, 1, 1 is an end device. And then you could have 0, 1, 2, 0, 1, 3, and they're all going to send their communication to the router 0, 1. And then if they want to send it to the base, to the coordinator, 0, 1 will handle that routing. So that's an introduction to it. Once again, in part 2, we're going to get into some of the code. Okay, here is my initial hardware design for the development board. Now, what I will say is this is a design, I'm doing this in real time as I create this series. So things could change, but this is the initial design I'm proposing. And so I plan to use the Atmega 328P. So that's the chip that's on the Arduino Uno. If you ever watch some of my other videos where I do an AVR/Arduino compatible circuit, you might recognize some of these things. So first off, I'm going to have this connection here to an FTDI cable so you can program it from USB to serial. That has some standard parts. It's going to link into the reset, through a capacitor. Here's my reset button that's connected through a 10 kilo ohm resistor to VCC. So every development board is going to have a temperature sensor. I'm going to use the DS18B20. In the past, I've used the TMP36 a lot, but this one's actually more accurate, and it does digital communication over a single wire. And there's an Arduino library for it. So I don't actually have any of these yet, and I haven't used them before, but I have some coming to me in the mail. And these are great because they're actually a little cheaper than the TMP36s if you're familiar with those, and they're more accurate. They offer a greater level of accuracy. Here I'm going to use an 8 megahertz clock. The reason is because I want to operate this circuit at 3.3 volts. And the Atmega chip can operate at 3.3 volts, but it can't operate at 16 megahertz. Well, actually it can, but that's not recommended. It's not in the stability zone of the chip. What I'm going to do is use 8 megahertz. And the reason I'm going to use 8 megahertz is because the Arduino Pro Mini has a similar profile where it has 8 megahertz and 3.3 volts. So that means when I add an Arduino bootloader to my chip, because I want to program using the Arduino IDE, I'll use the Pro Mini bootloader. Here I have a connection to digital pin 8 through a switch, and the reason I have that is because I'm going to have settings. I'm going to use the EEPROM on the chip, and I'm going to have settings that you can change. For instance, the node address. What else am I going to have in there? Oh, I'm going to have a different mode, so you can change it to router or to end device. And all these settings will be stored in EEPROM. And if I want to change one, I'll just use this switch, and I'll do it over serial communication. And the great thing about this is I don't have to load new code onto the chip to change these settings. So I'll show an example of that in part 2. Then I have on D7, I have an LED because I'm going to use this to sort of report certain states that the wireless sensor is in. For instance, if it's not, if it's transmitting and the receiver is not getting it, I'll have that light up. Here I have an analog pin connected to a voltage divider that's connected to the battery. So VCC is coming from a battery, and the idea here is I want to be able to measure the battery voltage so I know when the battery is getting too low, and the chip needs to let the coordinator know that its battery is going dead so you can change it. And the idea here is, if you've ever seen any of my videos on the Arduino ADC, I recommend checking them out, but I'm actually going to use the internal 1.1 volt reference of the Arduino. And the reason is I can't use the battery as the reference because the battery voltage will slowly drop, and this will just measure whatever the battery voltage is, so that won't be helpful. So I'm using the 1.1 internal voltage reference. That way I have a steady reference that the chip generates, and I can measure the battery voltage as it starts to drop. And the reason I have this voltage divider is the battery is going to be, let's say, 3.3 volts. As it gets lower, that's too high of a voltage to measure when you have a 1.1 volt reference, so I have this voltage divider here. Here's some standard connections for the Arduino. I have the VCC going into VCC, so you could use VCC as the ADC reference if you want. Then, of course, I have the NRF24 transceiver module that's connected to the standard SPI pins, as well as the CSN CE. I'll use D10 and D9. Here is my 10 microfarad capacitor to serve as an energy reservoir, so my chip has plenty of power when it transmits. Okay, there's the initial hardware design, and the point is I'm going to order these parts, I'm going to build it in Eagle, and we're going to get some boards to try out. Now going forward, I may change a couple things, but this is the standard design I plan to use. So some notes on the software. Now I'm not going to get into the software in this video. I have some initial software I'm working with, but I want to continue testing it. I mentioned this bootloader. I plan to use their Arduino Pro Mini bootloader. Here's the libraries you need to use, and once again, thank you to ManicBug for creating these and sharing these with the open source community. This is the standard NRF24. Here is the network version. If you have this RF24 library already, make sure you have the one from ManicBug, because there's a couple of versions people have created on GitHub. I had one that was not from ManicBug, and I got an error when I tried to compile it with the network.h. So just something to keep in mind. I mentioned how I'm going to use EEPROM to store settings. So EEPROM is like a hard drive. So I can store settings, and when the chip turns off, they don't get erased. So when the software starts up, you can go get those settings. So if you change those settings, the chip will remember it for you. I'm going to use the Watchdog timer, and I'm going to use sleep mode. So if you've ever seen my video series on power consumption and saving power with Arduino, basically what you'll do is I'll have the wireless sensors, the end devices, transmit data. I'll have the Watchdog timer, then first I'll have the chip go into sleep mode. I'll activate the Watchdog timer for some certain interval. So the chip is using very little power until it's time to transmit again. The Watchdog timer goes off. We come out of sleep mode and we transmit again. And then I also mentioned the ADC reference. I'm going to be using the internal 1.1 volt reference. Okay, and before I close, I just want to show you, I'm doing some initial testing, and you can see I have two boards that I made up. I have sort of the standard Uno board. This is actually going to be my coordinator, and then I have a Pro Mini here, and I have a board I made myself. Now, I will mention, shameless advertisement, this proto board for the NRF24 as well as this shield for the NRF24, I sell at my website, forcetronics.com, so you could get those there. I'll use this for the coordinator, but of course I'm going to have boards made up for the end devices. These are meant to just be test boards. So I wanted to sort of test the NRF network. So for my initial test setup, I have the coordinator here. This is my Uno. I have node 1, node 2, and node 3. And then I want to add another layer just to test that out. And once again, I'm going to test this more thoroughly. I just want to give an example of some of my progress getting started. And then I have node 1.1 here. So in my software, I basically have the coordinator reading temperature. I have a temperature sensor on each of these, and I'm using the TMP36 just for now, just to get started until I get my other one in the mail. I have it basically each sensor, or each node, I basically have it make a temperature measurement. I have it measure an open value in an ADC, so it's just an unconnected ADC pin, and then it's checking the battery status. Now I will say, right now I just have this hard-coded as a 1. I haven't tested the battery thing yet. I'll talk about that in part 2. But anyway, so each node is sending it, 3, 2, 9 is actually 1, and I'm not quite sure why the software reports it as 9 and not 1, and I'll have to dig into ManicBug's code a little more. So here's 1, 3, and 2, and then here comes 9, which is really node 1. And I don't know if this is an error. You can see 9 reported twice. So I need to figure out what's going on there. But I just have these on 1-second intervals just for test purposes, just to get the testing process started. Okay, that's it for part 1. Once again, just to give you a sneak peek of what I'm planning for this series, the basic goal to create a development board, a wireless sensor development board that I'm going to use in my house, that you can use the plans, or that I'll sell on my site. And then in part 2, we're going to get into the battery sizing. So what I mean by battery sizing is, right now I would like to use a coin cell battery, but I need to make sure the coin cell is going to last a long time for the end devices. So I think it will, but I want to do some testing and some power measurements to get an idea so I can estimate how long a coin cell will last if I use a coin cell, or if I have to go to a different type of battery. And then in part 2, we'll take a look at the initial code. If you're watching this and you have any questions or suggestions, especially suggestions on things I should add or something I missed, please let me know in the comments section. See you back for part 2, and thanks for watching.